So at the first part of this lesson, we're really going to talk about isomorphic vector spaces. But to do that, we have to introduce the idea of an invertible linear transformation because isomorphism is defined in terms of an invertible linear transformation. So a linear map is called invertible if there exists another one that you can compose. S composed with T is the identity, and also T composed with S is the identity. And in this case, we call S the inverse of T and write S equals T inverse. While that sounds really fancy, all it means is that you can go backwards. So if you look at this picture that we have, the pink arrows represent the linear map T, and it is invertible, which means that we can go backwards using the green arrows to get from an answer back to the input that gave us that answer, and we have a function. So if you follow a pink arrow and then a green arrow, you're back where you started. So that's doing the identity map. Doing T and then S gives you the identity map. And then also, if you do S, so if you take the green arrow first and then T, then take the pink arrow, you end up back where you started as well. So being invertible just means that you can travel those arrows backwards and think of yourself as a function. And that's basically the idea of being invertible. And then our fact says that a linear map is invertible if and only if it's both injective and surjective. So if we're injective and surjective, we call ourselves bijective. And then the question asks us, well, and what does this mean about the possibility of the dimensions if we're invertible? So invertible means we have to be injective and surjective. Why? Well, let's do the surjective part first. So let's break this function here so that it's not surjective. So I'm just going to draw a little dot over here. Well, what does that mean? It means that the S map, the green map, doesn't make any sense because there's no arrow coming out of that last dot. And S is supposed to go from W to V. So W is the domain for the green map. And everything in the domain you have to have the function defined for. So there needs to be some kind of green arrow coming out of that dot, which means the function has to be surjective. So you're surjective if and only if T inverse is defined for every element of its domain, which is W. So now what if I'm not injective? So I've added this extra domain element in V that's mapping by a pink map to the output that's right here. So that output has two inputs that are going to it, right? I can follow this pink map to get to the point, or I could follow this pink map to get to the point. But then there's a problem, because when I try to go backwards from the point in the point in W, and I try to go backwards to get to a point in V, I don't know which point I'm going to end up with, because I could follow the inverse for that one, or I could follow the inverse for this one. So if I think of the point in W as an input, there's not a unique output that maps with that input when I'm following this backwards, this inverse map. And that makes it not a function. So going backwards from W to V wouldn't be a function if our original function T, the pink arrows, were not injective. So we're going to be injective if and only if, well, T inverse has to actually be a function. So there has to be one output for each input in T inverse, which means that T had to have been injective, otherwise that wouldn't have happened. So we're going to be invertible if and only if we're both injective and surjective. So if we need to prove something's invertible, we can just prove that it's both injective and surjective. Well, then because it has to be both injective and surjective, we're pairing up the elements in the domain with the elements in the codomain, right? Each element in the domain is mapping with exactly one element in the codomain. So that would mean that for a linear transformation to be invertible, then the dimension of the domain would have to be the same as the dimension of the codomain. And so this actually allows us to conclude that if we have two finite dimensional vector spaces, they're going to be isomorphic if and only if they have the same dimension. So we don't even have to find an isomorphism between them to show that they're isomorphic. We know that such an isomorphism exists as long as they have the same dimension. So how can we prove this fact? Well, we know that if they're isomorphic, then there's an invertible transformation from V to W, but we just saw that if we were invertible, then that meant the dimension of V had to be equal to the dimension of W from that above statement. So that direction's already done for us. And then the other direction, if the dimension of V equals the dimension of W, we just need to create this invertible linear transformation, that's injective and surjective. But we can do it pretty easily because we know the dimensions are the same, so we can just set a basis for V and set a basis for W. So beta The VI's are going to be a basis for V, and gamma, the WI's, are going to be a basis for W. And then just send V1 to W1, V2 to W2, V3 to W3, and extend linearly. And certainly that's by definition injective and surjective, and therefore it has to be invertible. And so the two vector spaces V and W would have to be isomorphic. So if you have two finite dimensional vector spaces, then we're going to know that they're isomorphic if and only if their dimensions are the same. And we've actually kind of implicitly used this fact already. So example 1 asks us to kind of recognize that. It says, show that the vectors 2x squared plus 1, 3x squared plus 5, x cubed plus x squared plus x plus 1 are linearly independent, and explain how you implicitly use the idea of isomorphism in your conclusion. So here I set up the matrix like we typically do. I wrote, instead of 2x squared plus 1, I wrote 1, 0, 2, 0 because it's 1, 1, 0 x's, 2x squareds, and 0 x cubed, and so on. I did the same thing for 3x squared plus 5, and x cubed plus x squared plus x plus 1, and I row reduced, and I got a pivot in every column, so that meant that the original columns were linearly independent. And then I said that just means that those three polynomials are linearly independent. And the reason that I did that was I was using the isomorphism, right? I was taking the polynomial 2x squared plus 1 and treating it exactly like the vector 1, 0, 2, 0, and taking the polynomial 3x squared plus 5 and treating it exactly like the vector 5, 0, 3, 0. And taking the polynomial x cubed plus x squared plus x plus 1 and treating it exactly like the vector 1, 1, 1, 1. So I was treating the polynomial and the corresponding vector exactly the same way, and making conclusions about the vectors and saying they held about the polynomials, or wanting to talk about the polynomials but instead dealing with the vectors. That's because of that isomorphism. When two vector spaces are isomorphic, then we're really identifying the vectors through that isomorphism, and then the relationships between the domain vectors are reflected in their images, and the relationship between the codomain vectors are reflected in their preimages. So we're saying that they have the same structure, we're just kind of naming things differently. Instead of talking about 2x squared plus 1 when I'm in P3, I'm going to talk about 1, 0, 2, 0 when I'm in F4. But they have the same properties because of this isomorphism.